So welcome. Immediately lost my glasses. We'll find them. So welcome. So we're going to do this next bit, which is on Newton's laws applied to uniform circular motion. And we're going to have 4 different setups for this. But if you imagine in each case looking from above, you would see there's a centripetal acceleration because you're going in a circle. And there's a tangential speed. And then the circle has a radius. And there's only so many things I can do with this. At some point we need an equation to try and get us to an answer, so there's only so much I could do. But, you know, one time I could ask you what the velocity is, the next time I could ask you what the radius is, and so on. We say, consider a ball of mass m tethered to a string of length r. The ball travels in a circle with a speed v. The ball experiences centripetal acceleration that points towards the center of the circle, and this acceleration is caused by the tension force provided by the string. And the point I made last time was that you don't get a centripetal acceleration, so it's best not to think in terms of centripetal force. And sometimes the book does talk about centripetal force, and the problem with that is it's easy to get the idea that you get the force because you go in a circle. When in fact the centripetal force, if you're going to talk about a centripetal force, is a debt that you owe. And you must get it from some other thing. There must be something paying for that centripetal acceleration. And it must be some force in the same direction as the centripetal acceleration, or has a component in the direction of that centripetal acceleration. And so we start looking at the system and we say, well, in this case there's a tension in a string. Or for the moon and the earth there's a gravitational pull. Or for an electron and a nucleus there's an electrostatic pull. Or for a car going round a track there's a frictional force, points towards the middle. Or if you've got a bank track there's actually a normal force which has a component pointing towards the middle. But in each case you have a force you have a force that creates an acceleration that goes in the direction that you want. So I try not to talk about centripetal force. I talk about centripetal acceleration all the time, but not the force. My 2 basic equations, AC equals v squared over r and F equals ma. I try to draw my diagrams, no matter how they're drawn for me, I try to draw my diagram with the object on the left-hand side so that the acceleration is in a positive direction and the force causing the acceleration is in the positive direction. If you draw it in the other direction, just make everything negative, but what I worry about is that you'll spot one of the things should be negative and not another thing that should be negative. So it's just best to put them always at the left-hand side. There's 4 typical scenarios. There's soap on a rope. There's the next more complicated is that there's a level, flat, circular racetrack, and then the next more complicated is that there's a conical pendulum. It's basically a piece of string with a mass on it that forms a cone when you let it spin. And then the last and just you could argue the more sophisticated one is the angular track, the angled or banked racetrack. Let's do them. So first one, a 2 kilogram ball is attached to the end of a 4 meter long rope. So I'm going to draw a decent diagram like this. So let's have a look. That's 4 meters. That's 2 kilograms. The string can withstand a tension. And the tension, the maximum, the T max equals 80 newtons. It's the 80 newtons. It's the maximum value because it can withstand 80 newtons. And the implication is not 81 newtons. What is the maximum speed? So V max is what I want. And I know that my R is equal to 4 meters. I know my M is equal to 2 kilograms. So my velocity is like this. V. This is a decent diagram for looking down and above, but I really want to look from the side, so I have this. So this is 2, and this is my tension, and there's my AC. And yeah, there's a downwards force due to weight, but there's also an upwards force, because let's say it's going on a smooth table. If it's horizontal, the easiest way to get it horizontal is to be on a smooth table. Yeah. Sometimes that's not said. In this case, it's not said, but it's on a level table. So that's 220 newtons. This is Newton's laws. I say the sum of the forces horizontally is equal to ma. And it's not just ma, it's ma centripetal because it's going in a circle. And I know my centripetal force is centripetal acceleration is v squared over r. Okay, now look at my diagram. I've got plus t, that's all I've got, is equal to mv squared over r. My tension, it says my maximum tension is 80 newtons. So 80 newtons is equal to my mass, which is 2, v squared over my r is 4. So rearrange. V squared is equal to 4 times 80 over 2. Did I do that right? Yep. Which equals 3 eighths of 24, 4 eighths of 32, 320 over 2, which is 160. V is equal to the square root of 160, which is not equal to 40. I know sometimes when you're rushing you go, oh yeah, you see a 16 and you go 40. Second square root, 160. It's going to be 12.65. Now, it's asking for a speed, and a speed is a magnitude, so there's no need to worry about is it a positive sign or is it a negative sign. It's going to be the, if you like, no sign implying positive. It's not a vector that messed up there, didn't I? And that pattern, draw it from the side, recognize there's an acceleration, do the sum of the forces equals ma in that direction, and try and solve. That's what we're going to do for all 4 of these. As we get further on, we're going to find that it's not a lot. This is a one-step problem. They're going to be 2-step problems, We're just adding a little bit complexity each time. I could have given you the velocity. If you look here, I could have given you the velocity and asked you for the r. Or I could have given you the velocity of the r and asked you for the m. I can play with it, I could have told you the maximum speed you can go and said, what tension would that be? I got an equation, and I just got to make sure you have one unknown, So it's not always going to be this specific problem, but this is a type of problem. That's the same again. Let's make it a little bit more interesting. So now we have a circular racetrack. So let's draw it from above. And let's put our car over here. And the car is kind of like zooming along, so we have a velocity in that direction. And we've got to ask ourselves, well, what force is giving rise to this circular motion? What's making the car not just go in a straight line, which its inertia wants to do? And you say, well, when does a car go in a straight line? When I want it to go in a circle. And you say, on an icy road. If you ever lived in the north and you've turned your wheels and you get that horrible feeling where it's not going around the corner because you're on ice. So that's a lack of friction. And frictional forces always point in the direction where they oppose the tendency to motion. Frictional force is going to be in that direction. So there's my frictional force. I'm going to have a centripetal acceleration in that direction, and of course there's a radius for this thing. So I can turn around and say, what do I know? I know the mass is equal to 6 kilograms. I know that the radius equals 2 meters. Ooh, I know that my coefficient of static friction is equal to 0.8. What's the maximum speed? So V is what I want that the car can have. So there I have it. Let's draw this out again. So now I have my mass, and my mass is 6. And I have my weight downwards, which is 60. And I have my normal force, which is 60. And I don't really care about those, because we're at 90 degrees to where I'm going to look. I have a frictional force, which is in that direction. I don't know what that is. I can probably work it out. And I have an AC, which is in that direction. And then I have a radius, and I know that radius is 2 meters. And just so I have all the information together, I'll say my mu static is equal to 0.8. Just by the by, that's not a mistake saying mu static. I mean, you might think, well, the thing's moving, so surely he means the kinetic friction, not the static friction. But it turns out kinetic friction is when the two objects slide across each other. And when you're driving, your tires are not sliding across the road. They're being placed. If you imagine a little sticker on your tire, that sticker's not sliding across the road. It's been laid down and picked up and laid down and picked up and laid down and picked up and laid down and picked up. As far as the atoms on the road and the atoms on the tire are concerned, they get placed and lifted. They don't get slid. And in fact, when you do slide your tires across the road, when you lock your wheels and leave that skid mark behind, then your coefficient of kinetic friction takes over. It's not as good as your coefficient of static friction, so your brakes are not as effective. And that's why in modern cars they have ABS brakes to stop you from locking the wheels. And in my day, I was taught to pump my brakes when I was braking hard. You didn't just, you pumped your wheels to try and make sure you didn't lock the wheels up and go into kinetic friction. So the static friction there, that's not a mistake. That's what happens with car tires when you're driving properly. Okay. Let's just try it, the same old same. I'll try and solve it in one step. So I say, well, the sum of the forces horizontally. Remember, you've always got to have a direction. For Newton's laws, they don't work generally. They work in a direction. Each equation has to be in a direction. So I'm going to say, and the trick is, find out where your acceleration is and go in that direction first. That's the pattern. Look at your diagram, find out where that acceleration is and go in that direction. So I say the sum of the forces, the sum of the forces horizontally equals the mass times the acceleration. It's the horizontal acceleration. But this is not going to be just any old acceleration. This is the mass times my centripetal acceleration. I recognize this is the centripetal acceleration. And this is the mass times v squared over r, because that is the value of the centripetal acceleration. Just like I had last time. And now I look and I say, okay, FF is equal to mv squared over r. And the problem is, if you like, the only problem is, I don't know what my FF is. I can't substitute in for it because I don't know what it is. I've got two unknowns. So I can do a little side calculation. And I can say, let's just change colour pens. And I can say, well, let's have a look at this. I have 6, which gives me a 60 Newton weight. And therefore there's a Fn is equal to 60. If I was on a slope, I couldn't do that. But because I'm horizontal, that means my weight is vertically downwards and my normal force is vertically upwards. There's no horizontal, there's no sloping force to contribute, so I can just eyeball it and say 60 newtons down, 60 newtons up. And I know that FF is equal to mu times Fn. Well, I'm cheating there a little bit. It's FF is less than or equal to mu S times Fn. Remember that from before? But in this case, I'm talking about what is the maximum speed. The maximum speed is when I'm on the point of slipping. So for the maximum speed, FF is equal to mu S times Fn, because I'm on the point of slipping. It's as big as the force can get. Well, FF is equal to 0.8 times 60. FF is equal to 6/8 of 48. That's 48 newtons. So I have that. I'm going to do a little curvy thing like that. Then I come along, let's just change colour of pens again so that you know I'm doing a third bit now. And I say, well, in that case then, this gives me that 48 is equal to mass was 6, v squared over r, and my r was 2. So v squared is equal to 48 times 2 over 6. 6/8 of 48, so that's 8 times 2 is 16. So v is equal to the square root of 16, which equals, and again, we're talking about speed, which is a scalar, so I don't need to worry about the sign on this thing, and it's going to be 4 meters per second. So let's look at the commonality of this. We visualized, we did a diagram above, we made our list up, we did our diagram from behind. That diagram at the side, the one on the right hand side, is called a free body diagram, and that's the big thing that physics teachers kind of like get concerned about, is the ability to draw free body diagrams. There's a general feeling among the community of physics teachers that the game is won or lost in that diagram. If the diagram's right, there's a good chance you'll get it right. If the diagram's wrong or incomplete, most often incomplete. If the diagram's incomplete, you're kind of done. Doesn't matter how good your math is from that point. So the essence of the problem for most physics teachers is in that diagram. So we do that diagram, and then we say, we recognize there's an acceleration like we did before, and we write down our expression, Newton's second law, sum of the forces horizontally equals ma. We recognize that that a, in this case, is a centripetal acceleration, and we know the value for that is v squared over r, so we know its value indirectly. And then we try and solve, and what we find is, oh my word, you know, this is not going to work because I can't even substitute in for the first number, which is the FF. I can't have two unknowns. I can't have the v be unknown and the FF be unknown. I got to have numbers for these things. Oh, it's a two-step problem. And by trying to solve it in one step, the problem actually told me what to do next. I didn't have to remember that this was a two-step problem. I tried to solve it in one step, and the problem said, you can't solve this because you don't know FF. So then I scratched my head and I go, well, can I figure out what FF is? Oh yeah, of course I can. So I do that second little bit. So it's a two-step problem, finding FF. And then I substitute in and I'm on my way. So it's the same old problem, just this one number I couldn't find. I do a little side calculation to find that number, and I'm on my way. And that's the game we play. Okay. When I was a student, I used to think, oh, this is a special case, because it's longer, it's different, it's nothing like it. And now I'm a teacher, I realize it's the same old, same old. I just didn't know that number. Let's figure out that number, and I can continue as I am. And so there's fewer special cases when you view it like that. In both those questions, I asked you for the velocity. Again, just to remind you, I could have given you the velocity and asked you for something else. It's just just doing an example. You know. In this one, I'm asking you for the angle. And in a way, I'm asking you for the angle because this is a little bit more challenging. And although as a teacher, you kind of learn that it's not always good to do really challenging problems as the examples because people get lost in the challenge of it. Sometimes it's good to, when you've done a couple, do one that's a little bit more involved. So again, I could give you this angle and ask you for something else. And practically, it would be a bit more straightforward a problem if I'd done that. But I didn't, and so I'm going to try and show you this. It's just a little bit longer, that's the only thing. So let's visualize. So I'm going to, here's my circle. I'm looking down from above. Here's my bob, and the string kind of goes towards the middle, but it's not a flat situation anymore. And I have a tension, and I have an AC, and I have a velocity, and I have a mass. Same old, same old. Let's look at it from the side. I'm going to look at it from the side. I have a AC. And I don't have a force going towards the middle. But I do have a force going up the string. So that's a bit of physics kind of realization. The force is going up the string. I have a mass. So let me ask you a question. That's my free body diagram. Thinking about it, can you think of a force that acts on that mass that I'm just forgetting about at the moment? Is there a force that I'm missing? What would you call that force? Which direction does it go in? Weight. I just ignored the weight. It's not mentioned, of course, but now I have to think about it, and of course it's going to be mg, or I prefer to call it Fg equals mg, yeah? I'll get to numbers in a minute. Is there a normal force? There's no normal force because there's nothing, it's not supported by a table. This is in the air. So there's no normal force. Don't need to worry about that. I've got two forces, one acceleration. I have a radius. And the radius is r. So I'm kind of like building up my situation. Let's kind of put some numbers in if I have them. Let's change color for that just so I see. So let's have a look. 6 kilograms. So this is 6 kilograms. And end of a long string. The ball revolves at constant speed. Oh, I didn't draw my v in. My v is equal to 3 meters per second. It's a bit hard with these diagrams to draw. That, you know, when you're given the v, you want to draw it in. When you ask for the v, you might not want to draw it in. So I kind of draw it like that. I do my v like that to kind of just show it's coming towards me, you know. Okay, and then the radius is 4 meters. Let's just, whenever in doubt, do yourself a nice list. So m is equal to 6 kilograms, and v is equal to 3 meters per second, and r is equal to 4 meters. That's done. The ball rolls. That's done. That's done. Find the angle. So it says the angle between the string and the horizontal. Okay. There's a billion equations have the angle in, but I'm dealing with centripetal stuff. So let's start and say, okay, let's say the sum of the forces horizontally is equal to MA, which equals MAC, which equals mv squared over r. Now, let's look at this. Oh, I see. This is not a horizontal force, so I've got to find a horizontal force. I'm going to change colored pens again so you can see it. So there's my 4. I'm going to drop this down and put that guy in. So there's my horizontal component of my tension. And this is going to be t cosine theta. Can you see it? T cosine theta. It's the only horizontal component of anything. So I say t cosine theta is equal to 6 3 squared over 4. Well, that's oh no, you see, I don't know my tension and I don't know my theta. It's a two-step problem. Can you see how it tells me I'm a two-step problem because you don't know everything? So then I say, okay, well, we tried the horizontal. For the next step, let's try the vertical. Find T using the sum of the forces vertically equals, there's no acceleration vertical. If the thing is going in a horizontal circle, the acceleration must be towards the middle of the circle. Must be at least in the plane of the circle. Not pointing upwards, not pointing downwards. Because if it is, then it's not going to go in a horizontal circle. So this must be 0 vertically. If the acceleration is horizontal, there's absolutely no component vertically because it's 90 degrees. Okay, that's not so bad. So now I say, well, this is not in the vertical, but it has a component in the vertical. Let's drop that to that side and go like that. And let's recognize that this is t sine theta. So I say t sine theta. That's going in a positive direction. Added to minus, well, let's see if I can just write that in. Fg is going to equal minus 60. Because it's 6 kilograms. 6 kilograms mass gives me 60 newtons, so minus 60. There's my two forces vertically. Is equal to the 0. Oh, it's not so bad. So T is equal to 60 over sine theta. Okay, substitute n. Let's change colors so that you know it's a new idea. So I'm going to turn around and say, okay, we said t cosine theta was equal to 6 times 3 squared over 4. And I'm going to substitute in for the t. So this gives me that 60 over sine theta times cosine theta is equal to 6 times 3 squared over 4. And let's just work out that. That's going to be 3 3s are 9. Oh man, 1.5 times 9. Let's leave it as, let's just, well, I might as well work it out. 3 3s are 9, 6 9s, 5 9s are 45, 6 9s are 54. 54 over 4 is like 27 over 2, which is like 13 and 3/4? No, 13 and a half, yeah? Okay. So, we can say, next line, we say, okay, cosine theta over sine theta is equal to 13.5 over 60. Now, what is cosine theta over sine theta? Can you remember that? It's cotangent. And how did you get it? Did you just remember it or did you figure it? Okay, yeah. I can figure it. I'm not good at memory. So what I know is that adjacent, a cosine is adjacent over hypotenuse. And I'm dividing it by a sine which is opposite over hypotenuse. And that gives me adjacent over opposite. And then I remember, oh yeah, that's 1 over the tangent. Yeah? So I don't remember it. I know it's there, but I figure it out as I go along. It's like, I used to remember it. So this gives me that 1 over tan theta is equal to 13.5 over 60. So that tells me that tan theta is equal to 60 over 13.5. So theta is equal to tan to the minus 1 of 60 over 13.5, which equals, so I grab my calculator and I look to see I'm in degrees, and I go second tangent 60 divided by 13.5 equals, and I'm getting 77.3 degrees. And I got a little alarm bell going off in my head, so I'm just going to eyeball it for a second or two. So I flipped it. Yes, I flipped it. That's correct. Come down here, 6,3. Let's just check this. This is my m, which is 6, and my v squared is 3 squared. Yeah, that's 9 over r, which is 4. So yeah, that's okay. Yeah, I think that's fine. I don't think I made a slip on that. So I'm happy. Now let's stop in that. So I don't know what you feel about it, but it seems to me this math at the bottom is a little bit more mathy than, physicsy. It's not that it's not fair game. It's just that, it's like that's math. And there's a few lines of it, and you can make a slip easily enough. And you can't make a slip in a test, so I want to be careful about that. But the physics stuff is done above that, where the equations are. That's the physics stuff. And it's not obvious to me how you crack this egg to begin with. You want an angle, but, man, there's a lot of things can give you an angle. So what did I do? I said, from context, I'm dealing with centripetal motion. So let's begin the way we begin. Let's do the horizontal force equals ma. Oh, that's got an angle in it. I get it. And I couldn't solve it. So let's go back to basics. We always try one thing, and if it doesn't work, if it's not complete, we go at 90 degrees to it. So now I go and I try vertically. I'm using Newton's second law for the first bit and Newton's first law for the second bit. And then I say, oh, I get it. Simultaneous equations, 2 equations, 2 unknown, and I'm off to the cleaners, And this is something that one of my dear friends at USF is one of the faculty members I just think the world of, a guy called George Knowles. He's a really, really, really smart researcher. He's like in his field, he's world renowned. The guy's amazing. And he's also a really good teacher. And he was saying to me that one of the challenges that you have when you go into those upper division courses is that, now he's speaking specifically about physics, but there's some relevance to engineering as well. Is he goes, as the problems become more involved and more complex, you can no longer see your way to the answer at the very beginning. You can't just say, oh, I'm going to just do this and now I'm just putting numbers in. And so there's a leap of faith there in the, I know how to solve this type of problem and I'm going to start. And you rely on the fact that the math will take care of itself because you've got the math skills and you've got the analysis skills. If I don't solve it in one step, I'm going to go to 2 steps. So even though you might not know you're not going to solve it in 1 step, you know you've got that skill to be able to approach it in a 2nd step. And he said part of the issue is that when students first begin, they don't have the confidence about that. And so they freeze. It's like, I don't know how to do this. But that's not the question. The question is, do you know how to start doing this? And it's training students up so they've got more faith in. I got skills. I know how to start. Oh, now I know how to do the second step. Oh, now there's a third step. Oh, I'm solved. So it's that thing about being willing to kind of like sail out of the harbour and go over the horizon, having faith that you've got the seamanship skills to be able to find your way back again. And that comes with practice. It's not trivial. And so don't look at a problem like this and saying, I'm keeping away from that. Kind of look at that and say, I wonder if I could do it. I bet I could do that with practice, you know. And recognize it takes practice. I could have given you the angle and asked you for something else, in which case it's a bit more obvious what you do. Maybe it's a one-step problem then. I could have given you the angle in various ways, though. I could have told you the angle was 45 degrees or 50 degrees or something. I could have told you the radius, and I could have told you the length of string. I just gave you the angle. I didn't say it was an angle, but I just gave you the angle. So I could just give you the length of string and not the angle, and it's the same type of problem. It's just a different example of the problem. So again, don't get tied into exactly this problem. Don't remember this problem. Remember the approach to the problem, because that's what's gonna get you through. So a little bit more involved. Last little one. And this is the bank track. So the first thing we do is we draw a little diagram from above. And even though I've been nasty and drawn the little image with the banking on the right-hand side, you know, I want you to just get into the habit of doing the image with the car on the left-hand side. And it's got its velocity. And there's a force which causes a centripetal acceleration. But notice what it says, a 4-kilogram car, so this is 4, moves along a circular track that has a 5-meter radius, so you know that's 5 meters. The banking is designed so that the car does not rely upon static friction when traveling at optimum speed. That means there's no friction. There's no static friction. So we're not causing this acceleration because of the frictional force. Okay. If the track banking makes an angle of 20 degrees to the horizontal, what is the optimum speed? So now let's draw it from the side. So here we have and again, try not to draw a 45-degree angle. I have my centripetal acceleration. Can't you see how those multicolored pens would be really nice now? I could just click and get another color for an acceleration. I have a weight, of course. And this would be 40 newtons. Is there any force that I have not mentioned in my free body diagram? The normal force, and that would be perpendicular to the thing that holds the object. So that's my Fn. And it's not equal to 40 degrees because they're not in a straight line. It's not equal and opposite. It's going to be some component. And, you know, again, it's hard to draw, but I'm going to draw my V like that. You know, there's my V. It's coming towards me. Let's just do I like doing lists. I'm sorry, but I like doing lists. So I'm going to say my M is equal to 4 kilograms. The list just clarifies things in my head for me. The R is equal to 5 meters. My theta is equal to 20 degrees. And I have a V. Okay, I want to find V. The sum of the forces The acceleration is horizontal. It's a horizontal circle. So the acceleration is horizontal towards the middle of it, is equal to ma, which equals m centripetal acceleration, which equals mv squared over r. I look at my diagram and I say, well, there is no force that itself is horizontal, but there is a component of this Fn. And that component is Fn. I've got to do a bit of trig now. And can you see how, because I didn't make my angle 45 degrees, that's a little angle. And so is that. And so is that. So, 20, 70, 70, 20, 20, 70, 20. I can work it out, but I can see it if my diagram is sufficient. I can see, oh yeah, this is a 20-degree angle up here. I'm not going to make a mistake on that. Or if I like it, that's a 70-degree angle where the mass is. But I'm not going to make a mistake on it. But if I do everything at 45 degrees, who knows which one it is? So I look at this and I go, this is Fn sine 20. I can just see that. Again, if you're struggling with components, you've got to come and see me. Okay? So I say, and there's this 40 has no component horizontally. So I go plus Fn sine 20 is equal to 4, that's kilograms, 4 times v squared over r, and r is 5. Okay, so let's just, before I substitute and rearrange, let's just look at this. I got an Fn that I don't know, and I got a v squared I don't know. So I need to be able to find this Fn. It's a two-step problem. So I say, oh yeah, I can do this. Find Fn using, well, I've used the horizontal method, so we're going to say the sum of the forces equals 0 vertically. I used horizontal, so look vertically. I look vertically and I go, well, hold on. There's my vertical component of Fn, and this is Fn cosine theta. And this is 40. So I say plus Fn cosine theta added to minus 40 is equal to, is there any acceleration vertically? No. Oh, I see. So this is going to be Fn is equal to 40 over cosine, I know the theta, don't I? It's 20 degrees. I should have said 20 here. Yep. Yep. So it's cosine 20. Yep. So I look at that and I go 40 divided by cosine 20 is equal to, that's going to be 42.57. Again, I'm not going to round too much because I'm in the middle of a problem. Okay. So now I come back here. Color. Sorry, I'm having trouble with my colors. And I say 42.57 sine 20 is equal to 4v squared over 5. So v squared is equal to, let's have a look, 42.57 sine 20, I'm sorry, times 5 over 4. So that's going to equal, clear that up. I go 42.57 times sine 20, enter, times 5, enter, divided by 4, enter. So I'm going to get 18.120. So V is equal to the square root of 18.20, which equals second square root, second answer, 4.27. Yeah, 4.27, 4.266, 4.27 meters per second. Print a box. So, cool. So, that's another two-step problem. And I'm approaching them all the same way. I'm drawing a decent diagram. You've got to draw a decent diagram. And then I'm recognizing there's an acceleration there. And I'm going to do the sum of the forces equals ma along that acceleration. And I know the acceleration is centripetal, so I'm going to do a v squared over r. And then I try and solve. And then I find, oh, I can't solve. There's another thing I don't know. And the only other tool in my toolbox is I've got to go vertically. That's the only other tool I've really got. So then I look back at my diagram and I try and solve vertically, and I work my way through that. So 4 examples, and one of those types of examples will be on the test. But remember, I won't necessarily ask you about the velocity in this case. I might ask you about one of the other things, you know, what's the radius or whatever, yeah.
Would you give us this problem with friction involved?
No, I would not, because then it's a really complicated problem. If you're getting part of the solution from friction and part of it from the normal force, I think that's the kind of problem where it would, first of all, it would only tell me if you were at the very top of the game. So it's not discriminating from a class point of view. And secondly, it would take up so much time that it wouldn't be worth it to me in a test. I'd sooner just keep it that little bit simpler. So don't worry about that. No, you can try it for fun sometime, but you know, it's like, don't worry about that. Cool? Yes?
Actually, I realize that we don't have mass on these kind of problems.
Is it cancelling out? Yeah, sometimes mass cancels out. And sometimes what I'll do is I will just not give you the mass. Just, you know. Because if you're running your equations, you just put m in and you find, oh, m cancels. So that happens sometimes. Cool. That's the same thing. Okay. Let me have a look. I think this is the final little bit, and then we're done with this. Yeah. Maybe 2 final little bits. Probably not. How long we got? We got 10 minutes, maybe 1 final little bit. So supposing that my motion is not uniform. I'm speeding up as I go around a circle, or I'm slowing down. How on earth can I take that into account? It does not affect your centripetal acceleration. The speed does. So as you change your speed, as you get bigger speed, you will get a bigger centripetal acceleration. But at any instant, there's still a centripetal acceleration. Its value depends upon the speed at that instant, but it's always pointing towards the middle. Don't worry about that. What you're doing is you're adding to that model the next level of complexity, which is, well, now we've got an acceleration vertically as well, because we're speeding up or slow, not vertically, but in line, tangentially, because we're speeding up or slowing down. So under those circumstances, I have a independent, remember, 90 degrees means they're independent of each other. So I have a centripetal acceleration, which depends upon the actual speed, and I have a tangential acceleration which depends upon the rate at which my speed is changing, and I add them vectorially. So, of course, the classic things I can ask you is, what is the value of the overall acceleration? What is the angle to the centripetal or the angle to the tangential? Ask you those two things. And it's basically just using Pythagoras to get the actual value for the overall acceleration, and then using, you know, tan to the minus 1 for the angle. Let's do an example of that. At time t equals 0, a 3 kilogram particle travels at 8 meters per second around a circular path of radius 4 meters. Uh, 3 kilograms. 8 meters per second around a circular path of 4 meters radius. The particle has a tangential acceleration and the tangential acceleration is equal to plus 5 meters per second squared. What is the particle's net acceleration, and what is the angle between the particle's net acceleration and the centripetal acceleration? Well, there's my centripetal acceleration, and there's my net acceleration, A. Yeah? Find A using A is equal to the square root of AT squared plus AC squared. Agreed? Pythagoras. A is equal to the square root of 5 squared plus AC. Sorry, my phone's playing games with me again. AC equals V squared over R, which equals, I didn't make a list. Should have made a list. 8 squared over 4, which equals 8 times 4. 3 eighths are 24, 4 eighths are 32. Am I right on that? 64 divided by 4. 16. Duh. A is equal to the square root of 5 squared plus 16 squared, which equals, clear, 25 plus parentheses 16 squared parentheses equals 281. Second square root, second answer will back. Second answer 16, I'm getting 16.76. 16.76 meters per second squared. And then what's the angle? Particle centripetal acceleration, so it wants that for the angle. So tan theta is equal to opposite, which is AT over AC, which equals AT, we were given, AC we just worked out, so theta equals tan to the minus 1 of 5 over 16.76. Theta is equal to a clear second tangent 5 divided by 16.76 close brackets equals, I'm getting 16.6 degrees, which is none of those. So have I done something wrong? That's right, and that's right. Opposite.
It says the net,
Yeah, you solved for the
tangential.
wrong acceleration.
Oh, you're talking for the wrong acceleration?
It wants the centripetal on the net, not the tangent.
Centripetal and the net. No, that's what I did. Centripetal and the net. There's the centripetal. And there's the net. Oh, did I use the tangential?
Further down.
Oh, I used the tangential. Yeah. Rushing. So it should be 16, shouldn't it? It should be 16 and 16.76. That's my centripetal, and that's my net. So it's that, which equals 16 and that, which equals second, clear, second tangent, 16 divided by 16.76 equals, I'm getting 43. I'm going to just pause for a minute because I'm...
Are you supposed to use this?
Okay, I'm back. Yeah, I've been rushing at the end, so I was making a mistake. So what is the net particle's acceleration, and what is the angle between the particle's net acceleration and the particle's centripetal acceleration? So here's the net, and here's the centripetal acceleration, and we say cosine, not tangent. Cosine is equal to the AC over the A, adjacent over hypotenuse. So theta is equal to cos to the minus 1 of AC over A, which is cos to the minus 1 of AC, and my AC is 16, and my overall acceleration, my net acceleration is 16.76. So now I go clear, and I go second cosine of 16 divided by 16.76, enter, and I'm getting 17.32 degrees. I'm sorry? So, yeah, 17.4 and 16.8, so it's going to be A. Cool. So, sorry about rushing towards the end, and somebody in the class kind of helped me out by spotting it, so let's stop there.